begin the discussion of integration today, and as you know, in the undergraduate calculus courses usually differentiation is taught first and then that is followed by integration, okay. But logically speaking or even historically speaking, integration was discovered much earlier compared to differentiation. And if we look at the geometric interpretations, as you all know, that derivatives represent the slope of the tangent of a curve, whereas integrals represent the areas under the curve, and people knew how to find areas under the curve much before they knew anything about the tangents. Also the process of differentiation and integrations are in some sense inverse of each other, that is also something it is known, but from this geometric interpretation it is not immediately clear how these two are inverses of each other, and for that we need to go into the details of the theory of integration. So we will begin with what is normally called Riemann integrals. So here the idea is as follows: f is a function that is defined on some interval a to b, real valued function a to b to r, and we also assume that f is bounded. Okay. Since f is bounded, we can take some numbers which are the least upper bound and the greatest lower bound of this f. So let us say, suppose we denote those numbers by m, so let us say that m is supremum of fx for x in AB, and let us say small m is infimum of fx for x in AB. So in particular this means that for every x in AB, small m less than or equal to fx less than or equal to big M for every x in AB. Okay. Now the first thing to be done for this Riemann integral is what is called partitioning of this interval. Okay. So that is the next thing that we want to discuss, what is meant by partition or partitions. Okay. A partition of AB is nothing but, suppose this is the interval AB, we subdivide this interval into some subintervals. So and it is usually labeled like this first point A is called x0, this is called x0, let us say next point is x1, next is x2, etc., etc., and going like this, the last point B is called xn, and what we want is x0 should be strictly less than x1, x1 should be strictly less than x2, etc. So finally xn minus 1 will be strictly less than xn. So such a set of point is called a partition of AB. So this P, usually we denote like this: A is equal to x0 less than x1 less than x2, etc., etc., less than xn, and xn is equal to B. Okay. And since we may also want to refer to various partitions, we also like to give some notation for the set of all such partitions. So that we denote by script P, the set of all partitions of P, partitions of AB. Okay. Then let us now consider one such partition. Okay, some P in script P. So suppose it is this partition. Okay. Then for such a partition we look at, let us say, this xj minus 1 to xj, that is called jth subinterval. This is called jth subinterval. So there are n such subintervals. So whatever we have done for this full interval, we also do the same thing for each of those subintervals. That is, we look at supremum and infimum, this time not over the whole interval AB, but just for this subinterval xj minus 1 to xj. And it is obvious that if a function is bounded on the whole interval AB, it will be also bounded on the all such subintervals. So So we denote those numbers by big M suffix j, that is supremum of fx for x in AB, and small m suffix j as infimum of this for x in AB. Okay. Now having defined these numbers big M suffix j and small m suffix j, then we define what are known as lower sums and upper sums corresponding to this function f. Okay. So we will call it upper sum. Since this upper sum will depend on the function f and also on the partition P, so we denote that by UPF. This is nothing but sigma mj, that is multiplied by, okay, one more notation for this length of this jth subinterval, we denote that by delta xj. Delta xj is nothing but xj minus xj minus 1, okay, that is nothing but the length of jth subinterval. Okay. So that is, you take this number big M suffix j, multiply by that by the length of the jth subinterval and take the sum for over all such subintervals j going from 1 to n, that is called upper sum. Okay. Then similarly one can define what is meant by lower sum, that is denoted by LPF, L for lower, and instead of this big M suffix j we take their small m suffix j, sigma j going from 1 to n, small m suffix j delta xj. Okay. Now in addition to these upper and lower sums, we also have what is called a Riemann sum. Now here there is one more extra thing is required. What we do in this case is that we choose some point, suppose we call that point Tj in the jth subinterval xj minus 1 to xj. So we make that choice Tj in the subinterval xj minus 1 to xj, and instead of taking this number either big M suffix j or small m suffix j, we take the value of the function at this point f at Tj and then multiply that by delta xj and then take the sum for j going from 1 to n. This is called Riemann sum, and now the Riemann sum also will depend on P and F, but in addition it will also depend on the choice of these points Tj in the subintervals xj minus 1 to xj. So strictly speaking notation should be something like R, P, F and also some Tj here, but since that will make the notation very complicated, we do not usually include it here unless we have to make some specific reference to the way in which the choice is made. We will not bother about this. Okay. We will say that it is understood that Tj is any arbitrary point in the subinterval xj minus 1 to xj. Okay. Now before proceeding further, it may be useful to have a look at what these sums represent geometrically. Okay. And for example, suppose we have this interval a to b and suppose this is a graph of this function. Let us say this is the graph y equal to fx. Okay. Then when we subdivide this interval into subinterval, suppose this is xj minus 1 and that is xj, then it will be, okay, it is this subinterval. So this is f of xj, this is f of xj minus 1. Now what is small m suffix j? Small m suffix j is the minimum value of f in the interval xj minus 1 to xj. So let us say that will occur here. So that is small m suffix j. So this is small m suffix j. And what is big M suffix j? That is the biggest possible value of f in the interval xj minus 1 to xj. So for example in this case it will occur here. okay. So this will be big M suffix j and this will be small m suffix j. So when you multiply this big M suffix j or small m suffix j by this xj minus xj, let us take this case first, which will correspond to the lower sum, mj into xj minus xj minus 1, that will represent the area of this rectangle, okay, okay. And when you do it for all such subintervals, that is what you will get in the lower sum, okay. And similarly if you do it for mj, this big mj, it will represent this area, okay. What you will see is that each of this lower sum and the upper sum approximates the area under the curve. Lower sum approximates from below and the upper sum approximates from above, okay, and the Riemann sum is lying between these two, okay. So from the definition of this mj and big mj and small mj, it is clear that this f of tj, that is we small mj is less than or equal to f of tj, this is less than or equal to big M suffix j, okay. And lower sum is nothing but you multiply each of this number by delta xj and add, and similarly do the same thing for this, that you will get Riemann sum, and do the same thing for that, you will get the upper sum. So what you obviously have is the following, that is we get LPF is less than or equal to RPF, that is less than or equal to UPF, okay. This is obvious. One more thing we can see is that this big mj is a supremum over this subinterval xj minus 1 to xj, whereas this big M is supremum over the whole interval a to b. So this big M suffix j will be less than or equal to M, so this will be less than or equal to M into sigma j going from 1 to n delta xj, and this sigma j going from 1 to n delta xj is nothing but the length of the whole interval, which is nothing but b minus a. So this is M in big M into b minus a, that is in other words all the upper sums are less than or equal to big M into b minus a, okay. Or coming back to this picture, big M is the maximum over this or supremum over this whole, for example in this case something like this big M, okay. And so big M into b minus a is nothing but the area of this rectangle, okay. So all the upper sums will be less than or equal to area of this rectangle, and similarly one can say that lower sum PF LPF, that will be bigger than or equal to small m into b minus a. This inequality is true for every partition, okay. This is true whatever be the partition, this we can say always. What is the inequality? That is small m into b minus a less than or equal to lower sum, less than or equal to Riemann sum, less than or equal to upper sum, and less than or equal to big M into b minus a for every p in script p. Next what we do is we look at all these upper sums. So look at this set, okay, that is set of all UPF where p belonging to script p, okay. That is take all possible partitions and take upper sums corresponding to those partitions. Then we know that every upper sum is bounded below by this number small m into b minus a. So we can take the infimum of all these upper, see these are all numbers, for each partition you get a different number here, and this set is bounded below, so we can think of its infimum, okay. This infimum is a real number, so that is called lower Riemann integral, integral of f over the interval ab, okay, and it is denoted by this, I am sorry, this is called upper Riemann integral, okay, and it is denoted by this integral a to b fx dx. This bar over the above the integral sign denotes the upper Riemann integral, okay. Similarly if you look at all the lower sums LPF for P in script P, okay. That set is bounded above because every lower sum is less than or equal to this number. So we can take its supremum, that is the least upper bound, and that is called the lower Riemann integral. Okay, and that is denoted by integral a to b fx dx. It is lower Riemann integral, so we put one bar below, okay, below this integral sign. So that is lower Riemann integral. So once the function is bounded on the interval a to b, this upper and lower Riemann integrals, those will always exist, okay, and we can show subsequently that this will be always less than or equal to that, that is lower Riemann integral will be always less than or equal to upper Riemann integral. And so now we come to the main definition. When these two coincide, that is whenever upper and lower Riemann integrals coincide, we say that the function is Riemann integrable over the interval ab. So that is the definition, okay. F is said to be Riemann integrable over AB if this integral a to b fx dx, that is lower integral, is same as integral a to b fx dx, okay. And when this happens, that is when the upper and lower Riemann integrals coincide, whatever is the common value, that value is called the integral of f over the interval a to b, okay. So yes, yes. Oh, here x belongs to, sorry, okay, I will repeat that once again, okay. Big M suffix j, that is supremum of fx for x in that subinterval, x belongs to xj minus 1 to xj, okay, right. And similarly small m suffix j is the infimum of fx for x, okay. Oh, did I write AB here in the earlier? So that is wrong. This is correct. Okay, this is correct. Thank you. Okay, so coming back to this, when the lower and upper Riemann integrals coincide, we say that the function is Riemann integrable, and whatever is the common value, that is called the integral of f. Okay, so in this case, that is in this case means when the function is Riemann integrable, the common value is called the Riemann integral of f. Integral of f on the interval ab, and this is denoted by this symbol, just the integral sign denoted by integral a to b fx dx. This time no bar either below or above, it is just the Riemann integral of the function f. In fact, another notation for that is just this integral a to b f, okay. This is also convenient in many cases because you can see that this x really does not mean much, okay, because what is integral a to b fx dx is same as integral a to b fy dy or ft dt. So that is why this is simply called dummy variable, because you are ultimately summing or integrating over that variable, whereas the value depends only on the function f and on the interval ab, okay. That is why this notation is little more convenient, okay. Now before proceeding further, let us see some example of the function which is Riemann integrable and also a function which is not Riemann integrable. Okay, so let us just see example. Okay. Suppose we take the simplest example, let us say fx is equal to x, okay, or even simpler. Let us just take this. This also will involve little more work. Just suppose we take fx is equal to just a constant k, constant. That means fx is equal to k for all x in AB. Okay. Now if fx is equal to constant, then small mj as well as big mj over any subinterval will have the same value k. So that is what we take this UPF, whatever be the partition UPF, that is sigma j going from 1 to n mj delta xj. Since in that subinterval xj minus 1 to xj the function is going to be a constant, its maximum value is same as k. So mj is equal to k for each j. So it is nothing but sigma k times delta xj. So that k will come outside the summation sign. So this is the thing but k times sigma delta xj, j going from 1 to n, and we have seen that this sum is nothing but b minus a. So this is the thing but k times b minus a. Okay, and this k times b minus a is regardless of whatever was the partition p. So its infimum over, see this number is nothing but k times b minus a for every partition p. So its infimum also will be the same. So in other words, integral a to b fx dx, that is upper integral, this is nothing but k times b minus a. Okay. In a similar way, we can also observe that the lower integral, all the lower sums will also take the same value, that is LPF, which is nothing but sigma j going from 1 to n mj, small mj into delta xj. Since this small mj is also equal to k because the function is constant throughout the interval and hence on every subinterval. So this will also become k times b minus a, and so the lower integral a to b fx dx, again this is again also for every partition, for every p in script. Okay, so this will also be k into b minus a. Okay, and since this and this coincide, we can see that the function, this function is Riemann integrable and its integral is nothing but k times b minus a. Okay, this is of course a trivial example, but our idea here is to just explain the definition. Let us take one more example. Okay, so suppose I take the example, suppose G is defined as follows, G from AB to R. Suppose we define G as follows, Gx equal to, let us say 1 if x is rational and 0 if x is irrational. Okay. Now this time we will see that whatever subinterval you take, since it is going to take the, each subinterval is going to contain rationals as well as irrationals. So the minimum over each subinterval will be 0 and the maximum over each subinterval will be 1. Okay. So if you look at the upper sums, that is UPF sigma j going from 1 to n, big mj into delta xj, this big mj is 1 for each j because that is the maximum over the jth subinterval. So this value is nothing but b minus a. Okay, and hence, and since this is true for every partition, this is true for every partition. Okay, what we have is that integral, upper integral a to b, okay, this should be g because the function we are thinking of here is g. So upper integral gx dx, that is b minus a. Okay. On the other hand, if you look at the lower integral, or first look at the lower sum, so L P G, this will be sigma j going from 1 to n small m suffix j into delta x j, and this small m suffix j will be 0 for each j, because every subinterval is going to contain at least one irrational number, and there the function is taking the value 0. Okay, so this sum will become 0, and again this is true for every partition, and hence the lower integral a to b gx dx, this lower integral, this is 0. Okay, and so upper integral is b minus a and a lower integral is 0, so these two are different. So this function g is not Riemann integrable, g is not Riemann integrable. Okay. Now our next objective will be to, in general, now it is not possible to decide whether a function is integrable, Riemann integrable or not by using the definition like this and calculating upper integrals and lower integrals, except in some very special cases like this. Okay, for an arbitrary function, computing this upper sum and its supremum or lower sum and its infimum, etc., that will be quite difficult. So we need some verifiable criteria to decide whether a function is Riemann integrable or not. Okay, but before developing that, we will just consider one small extension of this idea, so that with little bit of more work we extend this whole concept to a little more general type of integral, and that is called Riemann-Stieltjes integral. Okay, Riemann-Stieltjes integral, and this Riemann integral is a special case of this Riemann-Stieltjes integral. Okay. Now what is happening here is that, okay, as usual, f is a bounded function on the given interval a to b, we take one more additional function, namely the function alpha, which goes from a b to r. Okay, and we take this alpha to be a monotonically increasing function. Okay, alpha monotonically increasing, Okay, let us recall that this means that x less than y, this means implies alpha x less than or equal to alpha y. Okay, that is monotonically increasing, and if we want to say strictly monotonically increasing, it will be in that x less than y implies alpha x strictly less than alpha y. Okay, for all x y in AB. Okay, and we make a small change in the definition of this upper sums and lower sums with where it comes to talking about Riemann-Stieltjes integral, and that small difference is as follows. This now this time it will also depend on this function alpha, so we should denote it by u p f alpha. Okay, that is sigma j going from 1 to n big M suffix j into what I call delta alpha j. Okay, delta alpha j is nothing but alpha at xj minus alpha at xj minus 1. Okay, so this upper sum is nothing but big M suffix j multiplied by delta alpha j, and similarly lower sum nothing but sigma j going from 1 to n small m suffix j multiplied by delta alpha j, and see with also Riemann sum R P f alpha, that is sigma j going from 1 to n f at tj multiplied by delta alpha j. Okay, you can see that why do we say that Riemann sums or Riemann integrals is a special case of this. It is because if you take the function alpha x equal to x, then delta alpha j is nothing but xj minus 1, which is nothing but delta xj, in which case this will simply become upper sum UPF, this will simply become lower sum LPF, etc. In other words, Riemann integral is a special case of Riemann-Stieltjes integral if you take the function alpha x equal to x, that is a monotonically increasing function. Okay. Now once having defined the upper and lower sums in this fashion, we also note the following inequality, namely that each lower sum, that is Riemann sum, will lie between lower sum and upper sum, that is LPF alpha will be less than or equal to RPF alpha, and this is less than or equal to UPF alpha. And as usual we can say that this, since this Mj is less than or equal to m, so this is less than or equal to m into sigma j going from 1 to n delta alpha j, and delta alpha j will be the thing but sigma delta alpha j will be the thing but alpha b minus alpha a. Okay. So this is less than or equal to big M into alpha b minus alpha a, and this is bigger than or equal to small m into alpha b minus alpha a. So a similar inequality, if you take alpha x equal to x, this becomes m into b minus a, and that becomes big M into b minus a. Okay. So that is why we say it is a small extension of the ideas, and as usual we define this upper Riemann-Stieltjes integral, as follows, that is again you take this set of all UPF alpha for p belonging to script p and take its infimum, that is upper Riemann-Stieltjes integral, and it is denoted by integral a to b f d alpha, okay, with this bar on top of the integral sign. Okay. And similarly we define lower Riemann-Stieltjes integral, okay. This time we take the lower sums, so LPF alpha p belonging to script p, and supremum of this is lower Riemann-Stieltjes integrals, that is integral a to b f d alpha with a bar below this integral sign. Okay. And as in the case of Riemann integral, we say that the f is Riemann-Stieltjes integrable if these two integrals coincide, okay. And whatever is the common value, that common value we will call the Riemann-Stieltjes integral of f and denote it by integral a to b f d alpha, that is without any bar. Okay. So we will just record that, this is the definition. F is said to be Riemann-Stieltjes integrable on AB with respect to this monotonically increasing function alpha, with respect to alpha, if these two integrals coincide. Okay. If integral lower integral a to b f d alpha is equal to the upper integral a to b f d alpha. Okay. And this common value is called the Riemann-Stieltjes integral of the function f, okay, with respect to this function alpha. Okay. The common value, that is whatever is the common value of the lower and upper integral, the common value is called the Riemann-Stieltjes integral of f. Denoted by integral a to b f d alpha. Okay. So now coming back to the problem of deciding which function is Riemann integrable or which function is Riemann tilde integrable, again as I said earlier, that requires some criteria or some tests, okay, and that requires some more work. So just look by this, just by using these definitions either of Riemann integrals or of Riemann tilde integral, it is possible to decide the integrability in case of very few functions, okay. But after going through some of these criteria and in particular some of the theorems, we shall be able to decide this question in case of a fairly large number of classes, okay. And to discuss that we need some more properties of these partitions, okay. So let us say that we take two partitions P and Q, suppose these are the two partitions, okay. Then we say that one partition is a refinement of the other if as a set Q contains P, we will say that, okay, this is a definition, okay, Q is said to be a refinement of P if P is a subset of Q, okay. What does it mean? That Q contains all the points of P and possibly some more, okay. Remember all the partitions must contain the first and the last point, okay, A is x naught and B is xn, those 2 points are there in all the partitions. In between whatever points are there in P, those are also there in Q, and perhaps Q may contain some more points. So what we want to know now is that suppose we take a refinement of a partition, then how do the upper and lower sums change, okay, that is the first thing, okay. So let us proceed to that, okay. Let us call that as a lemma. Suppose P and Q are the partitions, suppose P, Q are partitions of the interval AB, and F is, okay, and F from AB to R is bounded. Okay. Then what we want to say is that we want to compare these two, that is the okay, and alpha from AB to R is monotonically increasing. Okay. We want to compare the corresponding upper and lower sums of these two partitions, okay, that is we want to compare these numbers U P F with this U, okay, U of course in U P F alpha and U Q F alpha, and similarly the lower sums L P F alpha and L Q F alpha, okay. So what we want to say is that when we take a refinement, the upper sums decrease, that is U P F alpha should be bigger than or equal to U Q F alpha, okay, and the lower sums increase, that is L P F alpha is less than or equal to L Q F alpha, okay. To repeat again, whenever we take a refinement of a partition, the upper sums decrease and the lower sums increase, okay, that is what this lemma says, okay. Let us now see how we can prove this. Since if P is equal to Q, there is nothing to be proved, okay, then both these will be simply equal, okay. So let us say that Q contains some more points of P. To begin with, let us first assume that Q contains just one extra point, okay. Suppose Q contains one more point, that is one more point than Q, than P. Okay, suppose Q contains one more point than P. Let us say P is okay. Let us say P is A equal to x naught less than x1 less than x2 etc etc. Last point is xn and that is equal to B. And okay, let us look at the upper subs first. Let us say big M suffix j is supremum of fx x in xj minus 1 to xj. Okay, that is supremum is taken over this subinterval. Okay, let us just draw this picture. Suppose this is A is x naught, then we have x1, somewhere x2, etc etc, and this last point B is xn. There are some point x2 etc. All these points are there in Q also. Okay, all these points are there in Q also, but in addition there is one more point. Now that point has to be obviously different from all these points x0, x1, x2, xn. So since it has to be different from all these points, it cannot be A, it cannot be B, and it cannot be none of these xj minus 1 etc. So it has to lie properly in some subinterval. Okay, it has to lie properly in some subinterval. So suppose that point is, let us say that point is T. Okay, so let us say suppose T is the additional point. Now that point has to lie in some subinterval. So suppose that subinterval is, let us say, xi minus 1 to xi minus 1 to xi. Okay, of course the point T cannot be xi minus 1 or xi, it has to be properly between that interval. So suppose that point is T. So suppose T is the additional point. So let us say assume xi minus 1 less than T less than xi. Okay. Now look at the upper sums corresponding to the partitions P and Q. Let us, okay, let me write it here. Okay, sigma j going from 1 to, okay, let me write it first, UPF, that is sigma j going from 1 to n, big M suffix j delta xj, delta alpha j, okay. And UQF, that is, here we have to write somewhat carefully. Okay, UQF, what will be happen to UQF for writing that UQF for the interval x0 to x1, x1 to x2 etc, xi minus 1 to xi minus 1, similarly xi to xi plus 1, for all those other intervals the terms corresponding to this are the same. Okay, only difference will occur when you take this interval xi minus 1 to xi. Okay, xi minus, so for that what we will have to do is we will have to look at supremum over this subinterval xi minus 1 to T and T to xi. Okay, so suppose I give some notations for this. Okay, so mi, let us say mi star is supremum of fx for xi minus 1 less than or equal to x less than or equal to T. So that is the supremum over this interval. Okay, that is mi star. Okay, and suppose this I call mi double star, that is supremum over fx, this time it will be T less than or equal to x less than or equal to xi. Okay, so if you look at this UQF, for all j is not equal to I, the term is the same, and for the corresponding interval xi minus 1 to xi, it will be mi star multiplied by this T minus xi minus 1 and plus mi double star multiplied by xi minus T. Okay, so suppose we look at the difference between the two. Okay, basically we want to show this, that UQF alpha is less than UPF alpha. So we look at the difference between the two. So you look at u p f alpha minus u q f alpha. What will be the difference? The terms correspond, the difference will be because of this subinterval xi minus 1 to xi, because all the terms coming from the other subintervals are the same. So when you subtract, all the other terms are going to cancel, okay, and what is going to remain from here is this mi into delta alpha I. Let us write delta alpha in the full form, okay. What is delta alpha I? It is alpha xi minus alpha xi minus 1, that is because of this. And what comes from this? It is minus, okay, right, minus, it is mi star into alpha t minus alpha xi minus 1, okay, and plus, okay, plus mi double star alpha xi minus alpha t, okay, alpha xi minus alpha t. Here also yes, it should be UPF alpha, and here also UQF alpha, that is right, thank you, okay. Now what we can do here is that okay, we can write this same thing by adding and subtracting this term alpha t, okay. I can write this as, I can it is alpha xi minus alpha xi minus 1, I can say plus alpha ti minus alpha ti, okay. So if I do that, okay, you can see that it will be alpha, so I will just take this first, alpha xi minus alpha, I will take alpha xi minus alpha ti, this multiplied by mi minus mi double star, okay, and what remains plus alpha ti minus alpha xi minus 1, okay, that into here also mi minus mi double star, okay, sorry, mi minus mi star here, okay. Now the thing is to compare mi and mi double star. Mi is the supremum over this whole interval xi minus 1 to xi, okay, whereas mi star is supremum over this subinterval, okay. Let us also recall what is mi. Anyway, it follows from here, okay. Mi, you just take j is equal to I, mi is supremum of fx for x in the interval xi minus 1 to xi, okay. So the supremum over this bigger subinterval is obviously bigger than or equal to supremum over this smaller subinterval, okay. So that means mi is bigger than or equal to both mi star as well as mi double star, okay. And so, and alpha xi minus alpha ti, those are anyway non-negative numbers because alpha is monotonically increasing. So if you look at this sub, alpha xi minus alpha ti is bigger than or equal to 0, mi minus mi star is bigger than or equal to 0, and similarly here alpha ti minus alpha xi minus 1 is bigger than or equal to 0, and mi minus mi star is bigger than or equal to 0. So this whole thing is sum of two non-negative numbers, so this is bigger than or equal to 0, right, okay, and that proves that UPF alpha is bigger than or equal to UQF, that is upper sum corresponding to P is bigger than or equal to upper sum corresponding to Q. That means if you take a refinement, the upper sums reduce. In a similar way, one can show that lower sums increase, okay, because what will be the change? Here you will take small mi star and small mi double star. In that case, since we are taking infimum over a smaller interval, that will be bigger than or equal to infimum over the bigger interval. That is what we have to use, okay. Okay, now there is only one thing which we have assumed here. We have assumed here that Q contains one more point than P, but suppose you take an arbitrary case, Q contains let us say finitely many m points more than P, then you can take you can consider a partition Q1, Q2 etc. At each stage you contain one more extra point and then you go use the same inequality. So by induction we prove that if Q contains finitely many more points than P, then by the repeating this same argument that many number of times we will be able to prove that upper sums reduce and lower sums increase by taking the refinement. I think we will stop with that.